Well, good afternoon, everyone, and welcome back. I hope everyone has had a nice lunch. Welcome to the third session of today, where we will talk about recycling and circularity. My name is Nina Filen-Kallio. I work for Virol, and I'm also part of the Decompose project, where we're looking especially on the recycling of the wind turbine blades and how to make that in a more sustainable way. In this session, we have four interesting panelists. We have Jani S. Nielsen, who's the associate professor from Aalborg University. She's going to talk about fatigue reassessments for wind turbine towers. We have also Amok Gokhale from DTU Wind Energy. He's a newly Master of Science graduate from Sustainable Energy program. We also hopefully will have Henning Graman. He has experienced some technical problems, but let's see if he is available to give his presentation. He's the managing director of GSR Services, and talking about the role of IHM for decommissioning planning. And we have also Gaurav Sharma, who's the director of circular business models at Schneider Electric, and he's giving a also interesting presentation about how to really make business circular. So further ado, I would like to introduce Jani S. Nielsen from Aalborg University. Is Jani available?
Hello, thank you. So I will give this presentation on probabilistic. Okay, so can you see my screen now?
Yes.
Yes, okay, good, thank you. Okay, so I will give this presentation on probabilistic and risk-based fatigue reassessment for wind turbine towers. Okay, so just a few words about myself. So my name is Jani Sønderkjær Nielsen. I'm associate professor at Aalborg University. My research is concerned with reliability and risk-informed methods applied to wind energy. So both on relation to operation and maintenance, in relation to design, and in relation to end-of-life decisions. So what we are considering here is the decision scenario at the end of the planned life of the wind farm, which would typically be 20 to 25 years. So as you know, there are several options there, or there could be to continue operation without doing any changes, could be to do life extension, to do repowering or decommissioning. So if you are considering options where the intention is to reuse the substructure and the tower, and maybe change some parts in the rotor or the cell, well, then you like to know and investigate, does the tower and substructure have sufficient fatigue life for additional years of operation? So in order to do this, what most people would do is to do a deterministic fatigue reassessment. So apply updated data compared to the data used in the design. So doing a loads analysis and an operational analysis, and seeing if there are changes compared to what was assumed in the design. So then use a deterministic design equation as the equation that shown here, where we will have a number of load cycles and the time. We will have some SN curve parameters. We'll have some partial safety factors here, and then we'll have this damage that it depends on for onshore turbines on the distribution of the wind speed and the 90% quantile of turbulence, and this will usually be found using the aeroelastic simulations. But this is actually just the most simple approach, also called the semi-probabilistic approach. So if you look into this ISO 10294 standard on general principles for the reliability of structures, there are 3 levels, where the most advanced level is this risk-informed decision-making, then there's the reliability-based decision-making, and then this semi-probabilistic method, or deterministic, as it's also referred to. Where this reliability-based decision-making is then used to calibrate the safety factors for the semi-probabilistic methods. So the safety factors in the -1 standard used for design of wind turbines is found with this approach. And then in order to find what should the reliability target be, then can go to this risk-informed decision-making. But these approaches can also be applied directly for assessment. So if we go to this probabilistic assessment, then we'll need a limit state equation. As you can see, comparing this deterministic design equation with the limit state equation, they are quite similar. But here we have stochastic variables for this uncertainty on a minus rule. We have a model uncertainty on the load. And we also have this S-curve interceptor parameter as a stochastic variable. Then this fatigue damage is calculated based on the joint distribution of the mean wind speed and the turbulence. So this model that I show here, it was used to calibrate the partial safety factors for the deterministic method, so the safety factors in the -1 standard. And you can consider this deterministic design, this deterministic method as a simplification of the probabilistic. So I'll show here an example where we used the model that was used for calibration of partial safety factors, where a simple surrogate model is used for this load analysis, and then took the starting point in a design life of 25 years. What I did here was to vary the turbulence density. So if we have reduced turbulence, we would get a longer design life. And we would get that both if we used a deterministic assessment and a probabilistic assessment. If we get the same result for the 2 methods, we would have the lines here on this dashed line. But what I saw was that when we had the deterministic fatigue lives that were more than 25 years, we actually got even longer fatigue life from the probabilistic model. So indicating that without changing, without putting in a lot of new information, then you could actually verify that additional fatigue life by going into these probabilistic methods due to the way these partial safety factors are calibrated in the first place. You can also take a look at this target reliability. So the target reliability in this -1 standard for design of wind turbines is 3.3. This was found based on this table in this ISO standard on general reliability of structures with this risk-based method. So basically, it's an economic optimization where you maximize the benefit minus the cost, or just consider a minimization of the cost. So here, what's important is what is the consequence of failure, and also how expensive is it to make the structure more safe. So if it's expensive to make the structure safer, and also if the consequence of failure is small, then you can use a smaller reliability target. We can also show it with figures like this where we have the total expected cost here as function of the reliability index. What you can see is that if the reliability is very low, then you'll have large expected failure cost. However, if you increase the reliability, you will have an increase in the construction cost. So at a point here, there's this minimum. So this would be the optimal design point from a risk-based approach. And if you have that it is more expensive to increase the reliability, then you will have that this line is steeper. And you will get that this optimal reliability target is pushed towards a lower value. So if you have an existing structure, then it is much more expensive to increase the reliability. You might even say that, okay, so you can reuse this structure, so a substructure, or you would need to decommission it and put up a new one. So that would be much more expensive. So this, from the risk-based point of view, you could actually accept a lower reliability. If we look at the optimization in relation to life extension, we did a study here where we took the objective function as the expected present value of the profit, so the benefits minus the cost. So if we look at how costs are distributed in time, then for life extension project, then when the life extension is made, you have some cost to this, and then in the remaining lifetime there will be benefits from power production, and there will be some O&M cost. If we then had the case where there's failure in the lifetime, for example in year 7, then there would be no benefits after this point, so no power production. There would also be part of the O&M cost that would not be there anymore, variable O&M cost, and then there's could be some cost due to this failure. So we made a generic cost model based on cost distributed in time, like shown here, but considering then what is the probability of failure over time, dependent on the design. And what we could then see is that if we then vary this reliability index, what is then this expected present value of the profit? And you can see that it gets stable for very high reliabilities, and if we then start decreasing the reliability, it will drop, but it will not drop below 0 where it becomes infeasible unless we have very low reliabilities. So for example, a change from 3.3 to 3.1 will not make life extension infeasible, but this relatively small change, when you look at it in this way, actually gives a lot it will result in many additional years of operation. Here we see the annual probability of failure of a component designed for here a lifetime of 20 years, and increasing this reliability target, it corresponds to decreasing the reliability targets corresponds to increasing this target probability of failure to what I've shown here. So this could give 15 additional years of operation. If we could also take this risk-based assessment and apply it, consider a case study where we could approach this in 2 ways. If we could be allowed to use this reduced target, I showed before how the probabilistic assessment could result in larger fatigue life. But if we then use this decreased target reliability, you can see that it's even more years. Also, we did this direct risk-based assessment for a case study, where you could also see here that we see this only minor change in the expected present value of the profit if we reduce the target from, for example, 3.3 to 3.1. We have that, especially if we have a long, it was possible for other reasons to do a long life extension, then we will still have a lot of margin. So if we are looking at the repowering projects in light of these analysis studies I've shown here, then you can see that if we go to reliability-based assessment, it might be possible to show additional capacity by the use of a probabilistic method compared to when deterministic assessment is made. And if we go to a risk-based assessment, here we could argue that it can be much cheaper if we can reuse the substructure. So the cost of increasing the safety is high, and this augmentation could allow for a lower reliability level. So these methods, this is you can see there could be an economic benefit in this, but it's not only the wind farm owner that should be that we should consider here. What we should consider is that from the societal point of view, we also want to do this in a way where we optimize things from point of view of economic, but also considering the sustainability, and of course there's a clear sustainability benefit related to this. Okay, so thank you. I put some references here where you can read more about these things that I presented. Okay, thanks.
Thank you, Jani. That was definitely interesting, and also gives an idea about the complexity of the whole situation. Just as a reminder for our attendees that please, if you have any questions, put them in the question model on the right side, and we will address the questions to the presentators at the end of the session. So next we would have Master of Science graduate Amog Gogal from DTU Wind Energy, who is going to talk about decommissioning in general and have a bit of an overview about the topic.
Yes, Amog, if you could please just turn on your mic.
Yes, and are you seeing the correct screen?
Yes, we are. If you just go full screen, you're good to go. Precisely.
Just a minute. Yeah, is it visible?
Just a second. It's still working to go full screen, I guess. Try pressing escape. I think we had, yeah. Try going full screen again in the bottom of the screen, or just go into presenter mode.
I am there.
Yes,
is it visible now?
Yes, if you go to display settings and swap the two screens.
Yeah.
No, not yet. Try again.
Okay, yeah, I'll just duplicate it. It's fine.
We still don't see the full screen presentation. I'm going to try to take the presenter mode and give it to you again, okay?
Yeah.
There you go. And
I hope it's visible now.
Yes, we see a red screen.
Yes,
that's
perfect.
It. Okay, super.
Yeah.
You're good to go.
Yes, yeah, thank you. Yeah, first of all, yeah, thank you, Nina, for the introduction, and thank you all the previous presenters for the interesting insights into the topic. Today, I'll be briefing you about the recently published status overview report of decommissioning offshore wind farms, particularly focusing on the post-decommissioning or the disposal of the components and materials. Before that, just a little bit about me. I'm Amog Gokhale. I am a recent master's graduate from the Technical University of Denmark with a specialization in wind power. I'm originally from India and currently based in Copenhagen. So today I'll brief you about the status overview report, starting with the background information of the relevant topics. Then I'll inform the important assumptions that were done in this analysis and what type of data was required to go with. Then I'll showcase the case study which was analyzed and present the results of it. Towards the end, I'll conclude by mentioning the important results and any recommendations from the conducted study. So, decommissioning offshore wind farms. I'm pretty sure you have been listening to the talk since the morning, and you might have understood that till now there's only a limited practical experience, as there are only 5 commercial offshore wind farms have been decommissioned so far. So there are uncertainties regarding the process planning, vessel availability, regulations, and environmental impacts about this topic. But the DECOM Tools project predicts that within the next few years, more than 200 offshore wind turbines are soon going to be decommissioned. So the problem is soon going to increase. Currently, the disposal of the materials of the wind turbine and especially the blades is highly unsustainable, and that has sadly left a black spot on the image of wind turbines. So there is a need to improve this post decommissioning and material handling process and make the wind turbines as a fully green alternative. So this offers an opportunity to make the process more circular by implementing the principles of circular economy. So what exactly is circular economy? So it is an upcoming ideology which is going to be implemented in the whole European Union as well. So simplistically speaking, circular economy can be represented as a cyclical regenerative loops which start from taking some materials and making them into some product, using the product, trying to reuse it, remake it, and then finally recycling it back into the materials again. So in simplistic manner, circular economy is a closed loop system with the main goal of promoting responsible resource consumption, which can be achieved by maintaining the highest value through cyclical loops and increasing the product lifetime and process efficiencies to minimize the waste. So according to the circular economy principles, the processes with minimal effort to maintain the functionality of a product for a longer period of time are preferred. So in this analysis, different types of data was required, but mainly the material data of the wind turbines and especially the mass of them was gathered by assessing the 32 published life cycle assessment studies. So these studies have a list of materials present and used in the offshore wind farm, and also they state the quantity of it being used. So this data from different studies was aggregated together by using the power form of equation as shown here, where m is the mass of the material that is to be predicted, x is some parameter, it could be rotor diameter or capacity, and a and b are the curve fit coefficients. So by using these, and as we went ahead and saw that as copper, aluminum, magnets, and cast iron, these materials are mainly used in the nacelle of the wind turbine. The megawatt capacity of the wind turbine is the governing factor. Similarly, steel is mainly used in the wind turbine tower, so the hub height gives the quantity of steel being used, while the fiberglass and epoxy, which are mainly used for the blades, and therefore the rotor diameter was selected as the governing factor. A separate study was conducted to analyze the monopile foundations or the steel in the monopile foundations, which was seen to be varying with the capacity, and hence this was decided. So one of the main assumptions in this analysis was to consider the offshore turbine material equivalent to the onshore turbine material. And this was due to two reasons, as there's not much of a difference when it comes to just the turbine alone, for which is manufactured for offshore and onshore environment, And also at present, the data for offshore wind turbines is very limited. Now, the case study of Udgrunden offshore wind farm was selected for this analysis. This Swedish wind farm located in East Sweden had been decommissioned in 2018 after 18 years of its operational period. This wind farm consisted of 7 wind turbines of 1.5 megawatt capacity each, and they were supported by the monopile foundations. Now, I'll present the results for that particular Udgrunden offshore wind farm case study. Now, in this report, one of the main objective was to rank the materials according to different parameters and see which are the most important materials of them. So by ranking the materials used in the turbine according to the mass, the steel was seen to be the most used material. So the steel in the wind turbine combined with the steel used in the monopile foundations together accounted for up to 85% of the whole wind farm mass, while the magnets were the least used, with only a few kilograms being used per megawatt of the turbine. Now, these materials have certain monetary value in them, which can be gained by either selling them to the scrap dealers or recycling facilities. So the monetary value of these materials is calculated by considering how much of that specific material is going to be recycled and what is the rate as in euro per ton for that specific material. So by doing this analysis, cables were seen to have a quite large monetary potential, and this was mainly due to the presence of copper in them, while the steel in the turbine and in the foundations was also accounted for a large monetary potential just due to the sheer quantity of it being used. It is interesting to note that currently, on an average, at present the wind farm owner has some expense to get rid of the blades. So it could be either in terms of transportation or any other fees for that matter. So on average, it was seen to have a negative monetary value with the current technologies and regulations in place. Now, the recycling rate of the materials was assessed by assessing the studies which were conducted specifically for wind turbines. So the copper, cast iron, and aluminium, they have had a much higher recycling rate, and it's interesting to see that the steel, even though it has 92% recycling rate, the steel in the monopile foundations is assumed to have 50%. This is due to the reason that most of the foundation below the seabed is kept as it is. So it is as good as a material being left out of the system all alone. Also, it's required to note that current processes of treating the blades or treating the fiberglass and epoxy in them is mainly by using them in cement kilns for the heat regenerative purposes. So in that technology, it is not possible to get back the same material or get back to the fiberglass. So these processes are not considered to be recycled as in this report. The carbon emissions of these materials were calculated after considering the savings from recycling. So the magnets were seen to be the most emitting most greenhouse gas emissions, and it was interesting to see that the fiberglass and epoxy with the current technologies emit more carbon emissions by recycling than compared to the virgin production of them. So if we compare, say, different types of environmental indicators, the spread or the impact of each materials changes quite drastically as well. Now I will show some self-given ranks based on the research studies that were conducted. So firstly is the complexity. So the complexity depicts mainly how easy or how difficult it is to recycle a certain material. So the magnets, fiberglass, and epoxy are seen to be highly complex in nature, as there are not many commercially viable technologies that are currently in place. While cables are also complex due to the need of separation of plastics from the copper. Uh, the steel is fairly easy and it has been recycled since many decades, so it is fairly easy to recycle. But the steel in the foundations has to undergo some extra processes, so it has a bit more complexity compared to the steel from the wind turbine tower. Now, the criticality. The criticality is based on the economic importance and supply risks of a certain element for the European economy. So, based on the European study which was conducted, the magnets were seen to be the most critical material found in an offshore wind farm. So, this is because they are the raw material for them, the rare earth elements, are mostly found in China. So the magnets overall pose a huge supply risk. While the steel and the cast iron are also considered critical due to the vast extensive use of them in the European economy across various sectors. So to conclude, the assessing of different materials led to the conclusion like different materials being important under different parameters. For example, steel was important due to its quantity, while the cables were important due to their monetary potential, and the blades were important due to their complexity and mainly to maintain the image of wind turbines. The magnets are important due to their criticality and their large environmental impacts, and the foundations are important due to their regulatory aspects. So to do this, there has to be an increased focus on more effective disposal of these particular components and elements. So it is recommended to try to follow the disposal processes according to the circular economy principles. So as shown in the waste hierarchy diagram here, prevention of any material from being consumed, it's the most preferred option if compared to the disposal of the material into landfills. So in order to reduce waste, there has to be an improvement in the lifetime of the wind turbine. Also, an increased focus on reusing and refurbishing of the components is required, and not just limiting ourselves just thinking about recycling the materials directly. Also, there has to be an improvement in the supply chain for cables, magnets, and blades, as at present, not many industrial players are interested in those particular materials. Further research into foundation removal to see if it's actually better to remove them or to keep it under the seabed, and to see what are the different reuses that the foundation can be used for is quite critical. And lastly, the blades have to be remanufactured, or a focus on remanufacturing and refurbishment of blades is also required till we simultaneously develop a commercially viable recycling technology for blades. So I hope I was able to spark some more interest into the topic for you, and I'm open for questions towards the end. Thank you.
Thank you, Amok. That was a very structured presentation and gave also a good overview of the complexity and the difficulty of decision making, that what is the most important material in the wind turbines offshore, and how do we rank them. Next, we have Henning Grama from GSR Services, and he's going to tell us about the role of IHM for decommissioning planning. Go ahead, Henning.
Yes, thank you very much. I just tried to share my screen and I hope it works fine.
It does indeed.
Okay, that's good. I just see myself, which should not be the case.
You are in ideal mode to present now for us. So if you are ready, then you can move forward.
Great. Thank you very much. So yes, I listened with particular interest to the last speaker because this is basically where I'm coming from as well. But I even go a little bit further when it comes to the recycling. What I would like to present today is the role of the inventory of hazardous materials for decommissioning planning, which is a very focal point from my point of view. And we are not talking about the big structures. We are not talking about tons of steel, whatever. We really look into the tiny bits and pieces, which are very essential, basically, for ensuring a proper recycling. So who we are? We are compliance experts for the Hong Kong Convention and EU Ship Recycling Regulation. So it's not directly related to this topic of today, but I think there are some lessons which can be learned. We have a global network of 50 certified IHM experts, and we also do the recycling planning for ship owners and other maritime assets. So it is always a matter of time when anything becomes waste. And all what we see here, the wind farms, the ships, the supply vessels, all of them. So with this in mind, the IMO has developed the so-called Hong Kong Convention for safe and environmentally sound recycling of ships. And in Europe, we have a similar regulation, which is called the EU Ship Recycling Regulation. And both of them apply to all merchant ships above 500 gross tons, which means the supply vessels, quite a few of them, will be affected by this as well. But as I said, some principles can be applied to offshore wind farms as well, especially with regards to the inventory of hazardous materials and the recycling practices later on. What is my key focus? For the building and operational phase of ships, we look at structure and equipment. And here we have different hazardous materials which are of concern and which need to be documented for using them later on in the proper planning of the recycling process of these maritime assets. So for existing ships, all of them are affected as well. These inventories are to be prepared based on sampling and inspection under the responsibility of the owner, and he should involve a so-called IHM expert. For new ships, it is to be based on documents from suppliers, and the same applies also to the maintenance. So it's not only enough to get the IHM developed once and certified, it has to be maintained whenever any purchase takes place with regards to structure and equipment. And it is checked by the flag state of a ship, by the classification society, and also by the port state control. So for the wind farms, this is only partly applicable. What is very important is to be precise in the documentation, because this IHM, or Inventory of Hazardous Materials, has a status of a technical file, which means if a technical file is incorrect, the seller has to or might have to be put to court by the buyer because the technical description of this asset is wrong. So we have to take care that the samples are properly analyzed in a specifically accredited laboratory. But interestingly, the IHM only lists those materials where we have found hazardous materials to be contained therein. So that means all what has been checked, all the other suspicious materials, can only be found in the so-called IHM report, not in the IHM itself. And this is equally important for the recyclers and for the waste treatment systems to know what has already been checked and what has been found to not contain hazardous materials. The maintenance shown here in the middle, it's normal that ships buy stuff, materials, components, consumables, and if they are relevant for the IHM, they have to be accompanied by a supplier's declaration of conformity, SDOC, which is a supplier-specific document, and by a material declaration, which is a product-specific document, specifying the presence or absence of, in total in Europe, 15 different hazardous materials. This is just how the information is gathered. So on the left-hand side, the building yard or repair and conversion yard requests the MD and SDOC from the tier 1 supplier. And in many cases, tier 1 suppliers are just traders, not necessarily manufacturers, which means they have to get the same information from tier 2 suppliers, sometimes tier 3, tier 4. So, and during the maintenance, the same principle is applied. This is reflected here with a red arrow, which means the owner has to approach his tier 1 supplier in case of relevant purchases and has to request exactly the same documents until this maritime asset is brought to a recycling facility. So taken out of service and then sent over for recycling. How should the maintenance be done? Basically, all the orders have to be reviewed and categorized into relevant and not relevant. Only the relevant ones belonging to structure and equipment are followed up and requests are sent out to suppliers. Of course, these requests are monitored, and if the supplier provides the documents, they are reviewed. Still today, many of these documents are invalid, which means we go back to the supplier, explain to him what is wrong until we receive proper or valid documents. So these valid documents are categorized again. In most cases, more than 90% of all the documents, they are so-called 0MD, saying this product does not contain any of these 15 hazardous substances. These don't need a further follow-up. And in case the product does contain a hazardous substance, it's a so-called positive MD. And that means we provide guidance to the ship. And once they install this item, it has to be accompanied by feedback from the ship, meaning where and how much of this item or product has been installed. And that is then merged into the already existing IHM, and an IHM report entry is generated as well. This is a task from today on for the coming decade. So it's not done overnight. It's a constant process. So the IHM responsibility is clear. But what I would like to highlight is that the IHM has to cover the full life cycle of a ship or maritime asset from cradle to grave. How can it be used for the decommissioning planning? First of all, you get an overview of the bad news, meaning overview of the hazardous materials which require specific attention. And this should be used for the detailed recycling planning. So the construction and IHM specific aspects, for instance, are type and size. Where can we handle these, or the size, the mass of this maritime asset? What are the contained hazardous materials? Does the ship recycler has to deviate from its standard procedures because they are not properly designed or not properly taking care of specific circumstances each and every structure brings with it? So it's the responsibility of the owner to provide this data, including operationally generated waste and hazardous materials contained in spare parts, which are delivered to the recycler as well. And in case of ships, the ship has to be delivered in safe for hot work condition. So, and a final survey is required. As I said, this is relevant for ships, but maybe gives some ideas for the further recycling planning. The ship recycling plan, or let's talk about a recycling plan, has to close the gap between the standard procedure, infrastructure, and processes of the recycling yard to the individual construction of a ship or of a wind farm. So what is specific? How is it to be handled? Which means, how will it be delivered? How will it be secured in the plot or in the yard? How, and in each and every detail, it has to be described how the hazardous materials contained will be managed. Labeling, decontamination, packing, storage, and then finally disposal. And that also has an influence on the dismantling sequence. And in the case of ships, this has to be verified by the so-called competent authority. Just a conclusion on the IHM, which is in the shipping industry, unfortunately, highly underestimated at the moment, is the responsibility lies with the owner for the development and maintenance of the IHM. It is the basic document for ensuring safe and environmentally sound recycling, and also for planning of health, safety, and environmental aspects. Also, it has or it allows to have some conclusions on what is the specific training requirement and permit requirements for the yard, for the workers, or in some cases, some external specialists have to be called in as well. So without an IHM, at least in the shipping industry, no safe and sound recycling is possible at all. Thank you very much.
Thank you, Henning, for a really interesting presentation. I think that there is definitely much to learn from other industries and how they are doing things, and how can we then implement those also to the topics that are related to the wind industry and the recycling of the turbines. We have one more presenter today, Gaurav Sharma from Schneider Electric. He's the director of the circular business models, and will give us a really nice example of how a circular economy can be implemented as a real business inside the company, and also provide added value to the customers. After his presentation, we will have the Q&A session. Please don't hesitate to ask the questions in the on the right-hand side where it says questions. Then just type your question there, and also please write to whom you want to ask the question for. Then Gaurav, go ahead.
Thank you, Nina. You can hear me properly?
Yes, we can. And you're good to go with your presentation as well.
Okay, perfect. Let me just go back to my presentation. Okay, you can see my screen?
Yes.
Perfect. Well, thank you to the organizers, to Nina and all the previous speakers. Very interesting. I'm happy to share my part of this session with you. Thank you especially to Amog because you spoke about circularity, circular economy. So it's good. The base has already been built, and hopefully I can complement what Amog presented from another industry, electrical and electronic components that we do provide to wind farms. And how are we circular? What do we talk? There was LCA life cycle assessment spoken about. So I'm happy to show practical applications of what we can do. So a bit about myself. So my name is Gaurav. I work at Schneider Electric, where I lead the circular economy function from the global strategy team. I'm based in France. A bit about Schneider as well. So I'll tell you a bit about Schneider, how we fit into an overall wind farm landscape. What do we do for circular economy within the company and for our entire ecosystem, and a couple of concrete examples of that, and specifically of products that are being used in wind farms. So to start with, on Schneider, so we are the global specialist for energy management and automation and digital solutions. So electrical, electronic components, the software on top of them, we provide to various industries, various end users. From a wind farm perspective, we are present with our electrical and electronic components all over. When you talk about wind energy, how do you manage it? How do you make it safe and reliable? So that's what our products do. So as you see, main power circuit, medium voltage collection, etc. The reason is just to give you a context of where we are. And in the main power circuit, for example, at the bottom are some of the products that we do. I'll be focusing on 2 or 3 of these from a circular economy and environmental benefits perspective. So as you see, there's a low voltage circuit breaker for safety reliability, same for transformers, ring main units, or medium voltage collection parts. So just keep these in mind. The examples will refer to these, and these are available in wind farms all throughout. Moving to circular economy. So as I mentioned, Amog spoke about circular economy. So here I'll present to you from a Schneider Electric perspective how we define circular economy. So we split it into two main axes, upstream and downstream. So what you see on the screen, if you're aware, is part of the butterfly diagram of the Ellen MacArthur Foundation, which is a leading NGO for circular economy. We've taken part of it to kind of illustrate what Schneider Electric does. If I see on the left, so that is the upstream. So here you see the blue boxes, which is a simple value chain of mining, product design, manufacturing, distribution. The green boxes are our initiatives, examples of what we do at Schneider for that. Similarly, on the right side, you see the circular loops. So those are the ones that were mentioned by Amog as well as by Henning on what to do. Can we maintain, prolong? Can we do more circularity? So I'll come to those in a moment. So on the left, for example, what do we do at the mining materials mineral stage? We've taken a commitment to double recycle plastics in our products. So which means we're using more and more recycled materials rather than virgin materials mined from the earth. At the product design stage, we do eco design of all our new offers. We have something called a label called Green Premium, which ensures that there is environmental information freely available to the users of that product. So keep this in mind. This is the example I will be taking over the next couple of minutes. At the manufacturing stage, we have targets on zero waste to landfill, waste to resource sites. So all our big sites, we want to have zero waste, which means no waste should go to a landfill. Either we should reuse whatever's been wasted, we should remonetize, we should recycle, we should send it to other industries. And finally, at the distribution stage, there is sustainable packaging. So we want to have returnable packaging with our customers. We want to have recycled packaging. We want to have no single-use plastics in our packaging. So those are kind of the things we do upstream within Schneider at the design stage before the product reaches a user. So the upstream we call are what are the enablers for circular economy. Then we go to the right side, which is downstream. You see the loops over there. With the product or the system, can we maintain and prolong the life, reuse or redistribute, refurbish or remanufacture and recycle? It's kind of an inverted waste pyramid that Amog had showed. Of course, the inner loop, the inner the loop, the more beneficial it is for us, for the customer, for the user, and for the environment. We have similar targets and initiatives for the downstream offer. So the downstream is the execution. Upstream was let's enable this to happen, and downstream is actually to make it happen. So where we try to avoid materials, you see the first one, which is metric tons of primary resources avoided. So if we can do all this with our customers, with our end users, that means we are avoiding those many tons of material that need to be mined from the earth because we're keeping them in the system, so to speak. All this that you see on the right are services. So the product is always there with the end user. What are the services that can be provided to make sure it lasts as long as possible? And of course, there's also the matter of connecting these products to the cloud so that we know exactly what their status is and know which loop to apply when. For example, after 10 years, we can see a product has been aged, has been used quite a lot. So we cannot probably prolong its lifespan, but we need to refurbish it. That's the example. Now I'll take one example each of upstream as well as downstream from the products I showed you on the previous slide. So talking of upstream, so I won't go through the details of the slide. I had mentioned the Green Premium Eco Design label. This is the low voltage circuit breaker you had seen on the first slide. It's been designed in such a way to be circular. What that means is look at the two red boxes. So which means at the bottom, we say it is upgradable and durable. So to similar products of a previous range, it can be just plugged and played and the older products removed. So modernization can be performed without disrupting a big system in the wind farm. On top is the environmental information. So which means we provide transparent environmental information, life cycle assessments, end of life instructions. Let's see what they look like. So this, if there's a product with Green Premium, the user is assured of this. What is a product environment profile? It's a life cycle assessment for electrical and electronic products and HVAC, so heating, ventilation, air conditioning components. And it's based on ISO 14025. It's third-party audited. It can be compared with other products who have a life cycle assessment using the similar method. So that same product, we have something called a product environmental profile. In the middle, you see the bill of materials, which means the user comes to know, for example, for this product, it lasts on an average for 20 years. Its weight is 35 kilos. It has more than 50% of copper and steel in it, less than 15%, less than 10% of plastics. On the right side are the environmental impacts, and that's important. I'll just zoom in on that. So we're able to calculate and show during the, if you see the small text over here, manufacturing, distribution, installation, use. So during each phase of this product's life cycle, we're able to show an average amount of carbon emissions that were there. So during manufacturing, since the metals had to be mined, maybe since there had to be some manufacturing done, fuel had to be used, so there were some carbon emissions. Distribution, which means it had to be transported somewhere, there were some carbon emissions. So we're able to show on a base for the user how much are the carbon emissions for this kind of a product. Also, we provide end of life instructions. So at the end of a life, which means it cannot be refurbished or extended lifespan anymore, like Henning had mentioned, at some point in time, the product needs to be recycled. So these are freely available, the user or for third-party recycling companies to be able to properly do a green disposal of this product and properly recycle it. These documents are available freely on our website through our app. So basically it's for the user to be able to use them and be circular with them. So this was the enabler, as I mentioned. Now we go to downstream. What does this mean from a downstream perspective on the circular value propositions? So what we're able to provide, and you know, this is nothing specific to our company or our industry, overall for companies like ours, these are the three main models. We're able to extend a life, which is modernization. We're able to give a second life, which is refurbishment of products, and to handle end of life, which is collection and recycling. The two documents I showed you before, so the product environment profile with the breakup of what's in the product, what are the carbon emissions, can be used with these two offers. And the last one for end of life, it can be used for end of life instructions. I'll take quick examples of these first two, modernization and refurbishment. So first, let's look at modernization. If you see on the left over here, so that's modernization. It's the same low voltage circuit breaker example that I've given you. So what happens is we take out the old one, which is an old range, 20 years old. We put in the new one. And this panel that you see, the original cradle, doesn't need to be changed. And this is part of a big panel. What that means is the life cycle of that entire panel has been increased because we just changed one specific small component of that instead of changing the entire panel. And we can do the calculations. If you do all new equipment and or a retrofit solution, the graph on the top right, there is less material cost, less site cost, less downtime for this retrofit or modernization solution. And with the product environment profile, we can also calculate, thanks to that, what are the carbon emissions or resources saved. So here we've taken an example. It could be 135 oil barrels, some cars around the world, etc. 40 tons of CO2 saved because we were able to do this instead of change the entirety of it. So that's the example of retrofit or modernization. Similarly, we have refurbishment example. So I'll focus on the middle part over here. This is again the same diagram that you saw in the beginning, but what we use with the customer. So here, not taking into account the first or the third, I look at the second. So we were able to provide refurbished medium voltage products to a customer along with new. Because the fact it was refurbished, the customer had a saving on total cost. And we were able to calculate the metals and the carbon emissions also that was saved because we didn't create a new product mining the earth, but you reused or gave a second life to something that already existed. Again, the calculation was done thanks to the product environmental profile. So these two were good examples of we were enabled by the environmental profile and the design, and we were able to do downstream with the end user and show benefits not only of cost but of environment as well. So to sum up those two documents that I showed you, what could they do? I look at the 6 points over here. I already mentioned the first point, benchmark with other products using the same rules. Number 2 is the retrofit example I showed you of modernization. If we change just one small component in a big system and extend the lifespan of the entire system, there is a benefit. The third is we could check between two kinds of materials, which is greener. The example I like to give here is if we talk of a pallet to transport products, there's a plastic pallet and there's a wood pallet. So the plastic pallet, of course, is not greener because there were chemicals used. There was a more intensive manufacturing process. And the wood pallet is relatively greener. But over a life cycle, over 5 years, we might need 20 wood pallets, but only one plastic pallet. And that's where we need to compare this full life cycle assessment. Number 4 is what I already showed you in the previous example. If we use a refurbished product versus a new product, it's better in terms of environment in many cases. And the last two are what's coming in the future. With these kind of calculations, we're able to reduce the emitted CO2 because those could be costs in the future. Identify claims and revenues which are green. So this is to fuel into the EU Green Deal and the new CEAP, which is the Circular Economy Action Plan 2.0, which has been released by the European Commission also. So those are some of the benefits that could come out. And lastly, what we say, why is circular economy, circularity a winning strategy for all stakeholders? For customers, it reduces the total cost of ownership. Just as I showed you in the previous example, if we use refurbished instead of new, lesser cost. For the planet, it's a no-brainer. We're using less resources, we're mining less resources. For governments, it's interesting because it creates local jobs. All those circular loops that you saw need to be done more or less, except maybe recycling, need to be done on site, locally, near where the product is. And lastly, for businesses, it's beneficial because it gives a life cycle relationship with our customers. From a one-shot transactional relationship, we're able to be with them during the entire life cycle of the product. That's it from my end. I'm happy to take other questions along with the other panelists. Thank you, Nina.
Thank you, Gaurav. Really interesting to see this development that you are doing. Now I would like to invite also the other panelists to join into the discussion. Do I have also Yanni and Amok? Yes, we are all here. Okay, and now all the attendees, please, if there are further questions, then please write them in the question panel and name whom you would like to address the question. However, I will start with Yanni, if that's okay. Where can we find more information about the reliability-based assessment approach?
Well, at the moment there is no standards in this, but actually just yesterday we had the kickoff meeting in the committee for a new design standard on probabilistic design, the DAS9 in the IEC 61400 series. So we have just started the work. So within some years, there should be a technical specification on this. Until then. Well, there are some information in the links I provided in the presentation, where there's also some information in the DNVDL standards on life extension. So.
Okay, nice. So things are going forward also on that side. There is also a question for Gaurav. That what was the breaking point when Schneider introduced this new approach, and also in which year?
So thank you for that question, Nina. So we've been doing this for more than half a dozen years at least, and building it based on the products, because we're a B2B company. So our play in the circular economy is that they should be durable. It should be durable. We're not looking at shorter life cycle, more recyclability. We're looking at durability and long lifespan. So which means today what we're working on, the examples I showed you, are on products that are 20 years old. And we're able to do that. We're able to refurbish them. We're able to also replace them with new small components. So we've been doing it for a while, but in the last half a dozen years is when it's being called circular, and it's kind of started to explode.
Yeah, well, very nice that it has been like a business as usual already for a long time, but now it's just even more appreciated also by the other industry. That's nice. What about Amog? How did you come to the monetary potential of the materials that you used in your research? And could you elaborate a little bit more on that?
Yeah, sure. So the main part for that was to get the rate of, like, say, euro per ton of certain material. And after speaking with certain people, they said me, like, the London Metal Exchange, that sort of a referred site. So it's similar to stock market, where people have bids for that they need certain scrap, and the dealers have the prices like them. So it's a quite quite similar to stock market. So that was the basis to get the main rate of like the euro per ton of that specific material, and then calculating it with how much or what percentage of the material is being recycled, and then with those two figures you get to some monetary potential.
But that also means that once the price is changed, then it has a big impact on the economic perspective.
Exactly.
Yeah. Okay. Then there's also another question for Jani from Shaheen. Hi, Jani. Thank you for the interesting presentation. I was looking for the reliability indexes that you used. How did you assume these values for beta? Are they obtained through the experimental studies?
These are calculated based on a probabilistic model. So I couldn't share all the details in this presentation, but it is in these papers that I have referred to. So I've assumed probability distributions for these stochastic variables that are in the model. Then I have used Monte Carlo simulations to find what is the cumulative distribution for the time to failure, and based on this I can calculate the annual probability of failure, and from this I can calculate the reliability index. So it's
So that was well elaborated. Then how about Henning? Is this IHM a useful tool also for improving the recycling planning and practices in general?
Yes, absolutely. It's one of the core points for the recycling planning, just by knowing where are the hazardous substances. And this also has a big impact on whether or not we can refurbish, reuse, recycle materials, because if we don't have this information, we risk that we have that we end up with an unknown distribution of hazardous materials in the hinterland. What we need to see is we keep finding, for instance, asbestos in brand new components, even though it's banned in Europe since many years, but it's only banned in 70 countries worldwide. So the use or production of asbestos containing material has basically doubled over the last 30 years. And considering the international trading schemes from China, from India, from Russia, from many different countries, it's clear due to the lack of control in the countries where we have such an asbestos ban, that we can still find it sometimes in brand new manufactured items which are produced in Europe. So by testing and proper analysis, we get much more clarity and we avoid huge risk for the workers, for the environment, and during the disposal and dismantling in general.
And do you think that it's relevant only for the hazardous materials, or would you see that it should be expanded to all the materials that are used in the turbines or ships? Or
usually the recyclers know pretty well what are the valuable materials, especially in the shipping industry, and I think in all other industries like electronics, automotive industry as well. But for instance, the automotive industry is very unique. They are documenting each and every substance, no matter if it is hazardous or if it's valuable or neutral. So this is quite interesting, but the costs and efforts can only be handled due to the huge numbers of more or less identical cars. If we talk about offshore wind farms, if we talk about ships, they are more or less unique. So the costs would be far too high to really document, evaluate first, and to gather the data throughout the supply chain in this regard as well. So I think the bare minimum is to focus on the hazardous substances. It would be the ideal case, but it's extremely difficult to achieve that in these days, to have a full overview of the different substances used.
Okay, that was well elaborated. And what about Gaurav? I still have a question for you. What are the main challenges that you see in the entire ecosystem becoming more circular? Are we well on our way, or do we? What is hindering us at the moment?
Thank you again for the question. So that's my opinion, and based on the experience that I've had and our company's had, we're still at the beginning of the journey, especially when we talk of the entire ecosystem. A couple of key needs in that. One I already mentioned in the previous one. It's to do a sector-specific study on circularity. So what is applicable to one sector might not be applicable to the other. Today, what we see in terms of policies and circular goals is kind of one-step approach, which is not true. If there's a beverage manufacturer, for them, the recycled plastic in their bottles is circular if they can make it 100% recycled, which is waste recycling. For companies like ours, it's more B2B durability. So we don't see that today. And as part of industry bodies, etc., we're also trying to make that stand. There needs to be a sector-specific approach to circularity. And the other, of course, is around the finances and incentives. In many cases, it might be cheaper to actually create a new product than to take it back, refurbish it, and resell it. So if there are no incentives, because the system is still quite linear overall. So when you talk incentives, it could be, okay, is there a reduced social charge on someone who's doing repair or refurbishing services? Is there a reduced VAT on these kind of offers? So we don't see that difference today. So of course, from a pure simple economics 101, people will buy what makes the most sense to them. And there needs to be help from the policymakers on this.
Okay. And how do you see the balance between the cost reduction and sustainability improvement? Do you think that the customers are willing to pay, or is there a feeling of how much they are willing to pay more for a sustainable product?
I like to give an analogy of a cake in that. So we talk circular economy and what I just showed you in terms of circular value propositions. So the business benefits are the cake and the sustainability benefits are the cherries. So without the sustainability benefits, you still have cake. It's not as tasty. But without the business benefits, you only have cherries. There's no cake.
Okay. And maybe one last question for Amog. You had kind of like, you have the monetary potential, and then you had also the CO2 emissions as one of the key points of your research. How did you estimate the CO2 emissions of the materials?
Yeah, so basically, I mean, any material, it uses some energy, so it emits some greenhouse gases. So it was basically a calculation considering the primary production and if we recycle. So for example, if we say steel, so to produce 1 kilogram of steel, we emit 3 kilograms of CO2 in the air. But if we recycle the steel or make it by recycling the scrap, it only emits, say, 1 kilogram of CO2 for producing the same amount of steel. So in the end, the CO2 emissions were calculated considering the primary production and subtracting it with the recycled or the amount of recycling of the material that takes place.
Okay. Well, then I think we will finish this session, the last session of today. I would really like to thank Jani, Amog, Henning, and Gaurav for their time. And of course, all the attendees of today, of your good questions also during our sessions. And naturally, I would also like to remind you that we are continuing tomorrow, 10 o'clock again. And tomorrow we will go through topics like port and logistic strategies. That's the first session of tomorrow. And then we go to the cutting, disassembly, and removal. And the last session of tomorrow is submarine and power cables. So with these words, I would like to thank everyone, and I hope to see you all also tomorrow.